So in this session, we'll be discussing about the workspace in parallel manipulator. So the parallel manipulator motions, they can be restricted by different factors, that is the mechanical limits on the passive joints, the mechanical limits on the passive joints, then self collision between the elements of the robot and the limitations due to the actuators, limitation due to actuators and the singularity varieties, right? So these are the various factors that restrict the parallel manipulator motion, and these factors, they split the workspace into separate components. So the main problem with the workspace representation of parallel manipulator is that the limitations on the DOF. Okay, the limitations on the DOF. Hence, for the robots which are having greater than 3 DOF, there will be no possible graphical illustration of the robot workspace. This is not usually the case with serial robots. For example, the workspace of 6 DOF serial robot will be with the concurrent axis wrist may be represented by the 3D volume that may be reached by the center of the wrist. So this illustrates the translations and by the surface that may be uh, that may be reached by the extremity of the end effector. So which illustrates the 2 degrees freedom of rotation, freedom in rotation. The 3D volume, it depends only on the motion capability of the first 3 actuated joints, while the orientation, it will be using the uh, uh, last three joints. So a graphical representation of the workspace of parallel robots will be possible only for 3 DOF robots. For robots with n greater than, that is n greater than 3 DOF, the workspace representation will be possible only if we fix the n minus 3 post parameters. So according to which types of parameters are fixed or to the constraint we impose on the parameter, we will obtain different types of workspace. So there are different types of workspace. So let us learn the different types of workspace. So we have the constant orientation, constant orientation workspace, or the orientation workspace, then maximal workspace, or it is also called as reachable workspace, then inclusive orientation workspace, then total orientation workspace, then dexterous workspace, and reduced total orientation workspace. Reduced total orientation workspace, right? So these are the different types of workspace. The first one, it is the constant orientation workspace, or we also call it as the translation workspace. So all the possible locations of the operating point on the robot that can be reached with a given orientation. So that is the constant orientation workspace or the translation workspace. The second one is the orientation workspace, in which all the possible orientations that can be reached while C, it is in a fixed location. And the third is the maximal workspace or the reachable workspace. So in this, all the locations of the operating point C that must be reached with at least one orientation of the platform. And the fourth type, it is the inclusive orientation workspace. All the locations of the operating point C that may be reached with at least one orientation among a set of defined ranges on the orientation angles. That is the constraints on the orientation angles. So the maximal workspace, it is particular case of inclusive orientation workspace for which the ranges of the orientation angles will be 0 to 2 pi, right? Then the total orientation workspace. So in this, all the locations of C, it will be reached with all orientations among a set of defined ranges on the orientation angles. And the next is the dexterous workspace, in which all the locations of the operating point of the manipulator for with which all orientations are possible. So the dexterous workspace is a particular case of the total orientation workspace, and the ranges of the rotation angles will be 0 to 2 pi. Then the last one, it is reduced total orientation workspace. In this, all the locations of the operating point that may be reached with a subset of the orientation angles, and it may have any value in the defined range while others may have arbitrary values. Such a workspace may be important for applications that do not involve the degree of freedom of the robot. For example, if a 6DOF robot is used as a five-axis machine tool, right? As a five-axis machine tool, the pi orientation parameter is not important, right? So these are the different types of workspaces. So before we go into the orientation, or sorry, before we just go into the workspace calculation methods, we will discuss a few points on the how to represent the orientation. That is orientation representation. The most usual orientation parameters are the standard Euler angles, right? So which are denoted as psi, theta, and pi. This that is the pitch yaw and roll angles. So a problem with the Euler angles is that they exhibit a representation singularity for theta equal to 0. So the rotation angle will be then psi plus pi. So to solve this problem, we have the modified Euler angles. So that is the tilt and the torsion angles, which describes the orientation by first rotation by an angle pi around the z-axis, followed by the rotation above by an angle theta about around the y-axis, and then a rotation by an angle psi. So the torsion around the new z-axis. So the best way to represent an orientation workspace, there are three possibilities. That is, you can use the coordinate system. That is, the first one is the coordinate system, whose axis will represent the three Euler angles. And the second is the spherical coordinate system, where the pi and theta are the azimuth and zenith angles, and psi is the ray length, right? And the cylindrical coordinate system, where pi and theta are circular coordinates, right? Pi and theta are circular coordinates, and psi is the z coordinate. Okay. So there are three different approaches to calculate the workspace of parallel robot. One is the geometric approach, then the discretization method, and the numerical approach. So we will discuss the pros and cons of each method. So the geometrical approach. So here in this method, we will be determining the boundary of the robot workspace geometrically. So this principle is to deduce from the constraints on the each leg a geometrical object, that is WL. So that describes all the possible locations of X that satisfy the leg constraint. So one such object is obtained for each leg, and the robot workspace is constituted by the intersection of all WL. So consider for an example, so here 6 DOF UPS robot, and assume that the only constraint is that the length of the leg that has to lie in a range, say rho min and rho max. That is the only constraint given. So the extremity B of the chain is constrained to lie in a volume which is comprised between the spheres, that is with center A and with radius rho min and rho max, right? So if we further assume that the orientation of the end effector is constant, then each leg constrains the operating point to lie in a similar region. So whose center is obtained by just translating that particular AI by a constant vector BIC. So the workspace of the robot is then obtained as the intersection of all WI here, right? So if you also consider another example like a PRRS chain in which the prismatic actuator is connected by a universal joint to a link length L, and the volume that may be reached by B, right? So the volume that may be reached by B is constituted of a part of the cylinder which is of radius L and height rho max minus rho min, right? So this is topped by two hemispheres. This is topped, as you see here, it is topped by two hemispheres of with radius L. So if the orientation is constant, we can get WLI from the volume V by a simple translation, right? So this is the geometrical approach. So this approach, it is very fast and accurate, and it will provide a minimal representation of the workspace, which may be used to calculate efficiently some of the workspace characteristics such as volume. But it also have the drawback that it must be tailored to the particular robot, and it may be difficult to take all the constraints into account, right? So that is a drawback that you have in this geometrical approach. And the next method, that is the discretization method. So in this method, the workspace calculation is based on the discretization of the pose parameters, right? The discretization of the pose parameters in order to determine the workspace boundary. So in this discretization approach, the workspace is covered by a regular grid, either the Cartesian or polar of nodes, and each node is then tested to see whether it belongs to the workspace or not, right? So the boundary of the workspace is constituted of a set of nodes valid nodes, there at least one close neighbor does not belong to the workspace. So the advantage of this method is that it allows one to take into account all the constraints. In contrary to the geometric approach, you can take into account all the constraints, but this also has some drawbacks that the accuracy of the boundary, it depends upon the sampling step, right? So the accuracy of the boundary depend upon the sampling step that's used to create the grid, and also the computational step time, it will be exponentially increasing with the sampling step. So there is a limit on the accuracy, as because the computational time is also increasing with the increase in the number of sampling step, there is a limit on the accuracy, and the problems may occur when the workspace possesses voids, right? And next drawback is that the boundary representation also involves large number of nodes. Okay, so it involves a large number of nodes. So the boundary is used for different operations such as determination of the workspace volume, inclusion of a trajectory in the workspace, etc. When performed on a boundary represented by a discrete set of forces, these operations are obviously computationally very intensive, right? So these are some of the drawbacks that you have in the discretization method. And next approach is the numerical method. So so taking the constraints on the joint coordinates into consideration, the inequalities that are imposed by the constraints are transformed into equalities by means of extra variables. By using extra variables, the inequalities that were imposed on the constraints were transformed into equalities. So the generalized coordinates and the joint coordinates vectors. That is, let us take the generalized coordinates vector to be x and the joint coordinate vector uh, and the variable vector w, right? So they were introduced by the transformation of the inequalities into equalities, right? So this is the numerical method or numerical approach for determining the workspace. Now, by considering the 3 RPR robot parallel manipulator as an example, we will be deriving the workspace by few methods. So here, this is the 3 RPR robot which has 2 revolute joints and a prismatic joint at each leg. So the first approach, that is the constant orientation workspace. So we'll suppose that the orientation of the moving platform is fixed and we have to determine all the possible locations for a reference point C on the platform, right? So we will be assuming that the minimal length of the linear actuators to be rho min, while the maximum length of the actuators to be rho max, right? So as a result, the points BI that are located within the annular zone. So in the introduction, we have seen by geometrical approach how to just get that. So here, if you have two limits, the minimum and the maximum limits of the actuators, the point B, it will lie the point BI. So as you see here, B1, B2 and B3, right? So this point B, it will lie or located within the annular zone uh, with the external boundary being the circle CEI. CEI denotes the external boundary of the circle, which is having a center AI and the radius is rho max, and the inner boundary that is a concentric circle CI1, which is again the same with the same center but with radius rho min, right? So your point BI will be located in between these two circles, right? So since the orientation of the platform it is constant, when the point BI it is moving within this zone, the point C also moves with an analogous zone that is represented as WI. So this WI. So as you see here, it is W1, W2, W3. So this point C will be moving with respect to this zones W1, W2 and W3 with the boundaries which are circles CEI and CI1, right? So they are, as you see in this figure, they are represented as broken lines, right? So these broken lines, they represent CEI and CI1, right? The center SI, it will be obtained by translating AI by the vector B1C or BIC, right? So if the constraints on the link are satisfied, then the operating point C must be inside the workspace WI. So inside each WI, right? So if the constraints are satisfied. yeah, on a particular link is satisfied. So the workspace is obtained when the constraints on all the links are satisfied, and therefore the intersection of all WIs, right? So this area, what you see in the gray color in the second figure. So the intersection of all the WIs, that is W1, W2, W3, this is easily calculated. So the boundary of the workspace will be constituted of circular arcs from the three annuli. So as you see here, it will be circular arcs from the three annuli, right? So the workspace is deduced from these objects. So that is shaded in gray here. Okay. This is the workspace for the considered 3 RPR manipulator in constant orientation method. So the next approach for determining the workspace, dexterous workspace. So as we have discussed, the dexterous workspace, it is the set of locations of the reference point C for which any orientations can be reached. So it is the set of locations of the reference point C for which any orientations can be reached. So consider the same example of the 3 RPR robot, and let us take a consider a particular point C1 of this workspace. As all the orientations are possible, a point BI, it must be able to describe a circle with center C1 and radius of the norm of CBI, right? So this circle must be contained within the annular zone of the link I. So therefore, if we take into account only the constraints on link I, then the dexterous workspace is a circular annular region CAI, right? So and the internal and external radii will be, so the internal radii will be rho min I. So this we are writing for one particular link. So rho min I plus the norm of the CBI. Likewise, the external circle radius will be rho max I minus the norm of CBI. Right? So there is such a region only if the condition is satisfied. That is only if the rho max I minus rho min I is greater than or equal to 2 times the norm of CBI. Only if this condition is satisfied, then you can get an annular region with an external and internal radii as I have mentioned. So the dexterous workspace, it is the intersection of the three zones CAI. So this method may also include the constraints on the joints and the legs interference. So here in this figure, as you see, the dexterous workspace of C, it by taking into account the constraints on only one particular link, that with that you will be getting the, so the hatched lines here. So with L1 is equal to the norm of CP1, right?